Okay, so we've been talking Monte Carlo, Markov chain Monte Carlo, okay, MCMC. And so far, the example we've been using was a discrete case. We've had a discrete case, and the running example was visiting the islands on the island chain, right? Visiting the islands, okay. And we said the probability of moving, what is the probability of moving? It's the minimum between one and the other one, which is probability of basically our proposed location. So I think we said theta proposed divided by the probability of the current state, right? And basically either you're going to move or you stay. And if you stay, then your current position gets reused. Okay, so either move or stay. Okay, and if you move, the new location is recorded into your Markov chain, and if you stay, the current position is recorded again. Current location. Okay, great. So that was the discrete case. We talked about creating a transition matrix to represent, where you are and where you're moving to. And then we talked about kind of that based on that transition matrix, we can then find the stationary distribution, right? And what does the stationary distribution represent? The stationary distribution is the kind of distribution that you have where after you apply the transition matrix, you get back the same stationary distribution, right? So the stationary distribution, so if you have some stationary distribution W, then after applying the transition matrix, W times the transition matrix, you get back basically W again. So you get back the same stationary distribution. Okay. And the reason why this Markov chain Monte Carlo works is because the stationary distribution of your transition matrix is your target distribution. Yes. So if we have in our case with the 7 islands, we have we had 7 islands, and this you're going to have some kind of starting distribution here on where you started off, okay? And then you apply the transition matrix and you'll get something different after that, okay? The stationary distribution is where if you have some probability set and you apply your transition matrix to that stationary distribution, you don't get back something different, you get back the same thing. Okay? Meaning, what that means is, you know, in the stationary distribution, those leaving state 1 going to other states is equal to all of the other states that come back to state 1. Okay? And then at state 2, you have, you know, for each of these states, you have, you know, if you have state 2, you have people leaving state 2, going to any of the other states, and then, but you also have people coming back to state 2. And under the stationary distribution, the people leaving state 2 and the people coming back to state 2, those even out, okay? Therefore, so the stationary distribution is where you've reached this complete stability in that everybody leaving is equal to the people coming back, right? And so it's kind of, I think earlier on we had this idea of people can move from California to Texas and people can move from Texas to California. You know, we have stationarity or stability is reached when the number of people moving from California to Texas is equal to the people moving from Texas to California, okay? And when those two numbers are equal, that's your stationary distribution, okay? And so you apply the, you know, the transition matrix from one to the other, and if you get back the same thing, that's your stationary distribution. And what we can show is that when you have this transition matrix, which is determined by kind of the rules of the Metropolis algorithm, then you can show that the stationary distribution of that transition matrix is equal to your target distribution. Okay, so MCMC works. Because the stationary distribution of the transition matrix is the target distribution. Okay, and I think, and I'm writing up your homework 3 assignment, and in your homework 3 assignment, I'll have you guys kind of explore this and, I don't know, work things out a little bit numerically to I don't know, to enhance your understanding of this rather than just taking my word for it. Okay? All right. Is this okay? Are there questions on this? We're okay? All right. So let me, so this is everything for the discrete case, okay? And the Metropolis algorithm, and really Markov chain Monte Carlo, this works best when you have, well, I want to say it works best, but what makes it great is that it works in, you know, continuous cases and multivariate cases, okay? So here I'll show you kind of how the Metropolis algorithm works in a continuous case, and again we'll start with just one variable, and we can see kind of how this works, okay? And it's the same idea here, except we're just kind of building up, and we'll get to where we want to go. Because obviously, if we have the ability to evaluate probability of the proposed location and the probability of the current location for a discrete case, and there's only 7 cases or only a certain number of cases, it doesn't make sense to try to use the Metropolis algorithm, okay? It makes sense to use it in a high-dimensional case where it's hard to sample directly from the target distribution. But let me just show you kind of MCMC for the continuous case. Okay, and one of the big advantages here is we only need to be able to evaluate f of x, and f of x is proportional to the PDF, target PDF, I should say. Okay, so you don't even need to evaluate the target PDF directly. You just need to have something that's proportional to the target PDF. Okay, and this is a very common scenario in Bayesian probability or Bayesian statistics. Okay, so if you'll recall, so we'll start with Bayes' rule. Okay, Bayes' rule is that the probability of A given B is equal to the probability of A and B divided by the probability of B. And this is equal, probability of A and B can be found doing the probability of B given A times the probability of A divided by the probability of B. Okay, so in when we apply this to kind of, parameter estimation, the idea is, you have data comes from some model with parameters theta. Okay, so you have data coming from some kind of model with parameters theta. So for example, you could have data coming from a normal distribution with mu equal to 100 and standard deviation equal to 15, and in that case your theta is equal to kind of the set 115 representing your mean and standard deviation. Okay, so anyway, we have basically what we have X, our data, okay? And we want to model, we want to know the probability of our parameters based on the data. This is known as the posterior distribution. We want to know what's the probability of the distribution of parameters based on the data that we have. Okay. This is what we want to know. I hope this is all right. If I'm doing anything too quickly, please slow me down here. Okay, so we want to know the distribution of theta based on the data we have. And what we're going to do is we're going to apply Bayes' rule. So we want to know theta based on x, and we apply Bayes' rule to get this. Okay, so applying Bayes' rule, we have the probability of theta given x is equal, and using the Bayes' rule here, I got the probability of x given theta times the probability of theta divided by the probability of x. All right, is this okay? And x given theta, this is easy to compute, right? This is the x given theta part, that's our likelihood. This is basically, it's just the probability of your data when you plug in some set of parameters. Okay, so I'm going to just kind of flip to the next slide. So this is what we are going for. We want to know what is the probability of theta given x, and probability of x given theta, this is the likelihood. And this is easy. This is easy to find. So, for example, we can say, if we're x comes from a normal distribution with, mean equal to some value, okay? I'll call this theta sub 1 and standard deviation equal to theta sub 2, then we can find the probability of x, right? This is just basically the PDF of the normal for x given theta 1 and theta 2, right? So you would just plug in R, this is the equivalent of d norm, and you plug in your x value, and you plug in mean equal to theta 1 and standard deviation equal to theta 2. This is just the density of, it's the value that the PDF returns for a given set of parameters on x, for x, okay? So this part is easy to find, yeah? And then in theta, this is probability of theta, this is your prior. So you might have some kind of, this is the prior distribution of the theta parameters. Okay, and so you could say, I think theta for the mean could be, anything between 0 and 1,000, and everything's equally likely. Then you have a uniform prior on the mean. Or you might say, well, my prior opinion is that values around 150 are more likely. And so you create a prior distribution on theta. Now, if we were to do this analytically, there are what we call conjugate priors, which have nice mathematical properties here. But because we're doing this computationally, we don't have to respect the conjugate priors. There's a lot of reasons why you might want to choose a conjugate prior, which has all of these nice mathematical properties, which make the computational part easier. But we can use whatever prior distributions we want. Okay, we can, the prior distribution of the theta parameters. This basically this just represents our quote beliefs about theta before seeing the data. Okay, so let's say, and you would just take into account kind of your, I don't know, knowledge of the world, right? So we could say, we want to, based on when people, trying to figure out life expectancy numbers, okay, your current estimates on life expectancy is probably something around 70 to some number around there, and you'd say, okay, well, I'll create a distribution around 70, probably going somewhere from like 60 to 90 or something, where I want to make a peak around 70, and you can make up just some curve to illustrate this, or you can try to find a distributional curve that kind of represents something like that. Okay, and that just goes into the prior. Okay, again, there are what we call conjugate priors, which have nice mathematical properties, but it doesn't really matter. Okay, and then the bottom part, px, this is called the marginal, and this is the hard part. This is, what is the probability of getting this data across any set of possible parameters in the universe? Like, what is like every single, like, if we knew nothing about the model that generates all of this data or something, what's the probability of just getting this data? Okay, that's the probability of the data across all possible ways to generate the data. Okay. of the data x across all possible models that can generate x. Okay, and this is very difficult to compute. Okay, unless you've picked a conjugate prior with some nice properties and everything like that, you know, the marginal distribution, that's hard to compute. But the beautiful thing about Markov chain of Monte Carlo is that you don't need to figure this out. P of x does not depend on the data, does not depend on the parameters theta, okay? This is with regards to the parameters that we're trying to estimate. This is a constant. It is something that's fixed to the data that we've seen, okay? So P of x is just a constant. Okay, and so we can kind of ignore it, okay? Because if we just say, well, f of x is just equal to the numerator, and we don't bother with this, this satisfies what we're dealing with. We don't have to worry about the denominator, okay? Okay, so, you know, we don't have to worry about calculating the denominator. Actually, it's, I guess, f of theta. Okay, so that's what we have. We just say, you know, the probability of some proposed value theta is just proportional to this. Okay, and so we can use this to create our Markov chain. All right. So we have an example with the beta distribution trying to estimate parameters for a binomial distribution. Okay, and I don't know how familiar you guys are with this. Okay, and so the idea here is, you know, you observe somebody flip coins, okay, and the question is, how do you estimate the proportion, the probability of the coin flip, right? So basically a coin, we say a coin lands heads with probability equal to theta. This is the proportion that the coin lands heads. And you know, we observe some coin flips. And based on the number of times it comes up heads, we want to estimate this probability theta. And if we were not doing this a Bayesian way, we would do this the frequentist way, and we would probably use maximum likelihood estimation. And we'd say, okay, the coin landed heads 6 times out of 10, therefore, and you guys learn maximum likelihood estimation, right? In like 100B or something, you know, you try to find the value of P that maximizes your, or theta, that maximizes the probability of your data. And you say, okay, well, based on the likelihood, if it landed head 6 times out of 10, p hat is 0.6. Okay, and our estimate, our maximum likelihood estimate is just 0.6, and then that's it. With the Bayesian case, we create a distribution. We say, I'm not ready to just settle down on a single number. I'm going to create a distribution, and that distribution is a combination of the likelihood which is maximized at 0.6, and my prior beliefs about coins, which is that I'm pretty sure that most coins land heads 0.5, but you know, I don't know, perhaps I'm suspicious of the coin or something. You know, maybe I'm open to the possibility that the coin is doesn't land heads with probability of 0.5. Okay. And so our posterior distribution, probability of theta given our data, is a combination of our likelihood times the prior. Okay. Now the likelihood, this is going to be kind of the a Bernoulli distribution. With parameter theta. I'm gonna stop this. Close the poll here. And then what we have here is the prior distribution. And the prior distribution for a coin flip, the conjugate prior is the beta distribution, but you know, so I'll use that here, but we don't necessarily have to use that. Okay, so this is the beta distribution with parameters, with shape parameters a and b. Is anyone not familiar with the beta distribution? So the beta distribution, its support goes from 0 to 1, and you know, depending on what your distribution looks like, it can look like it can look like this. It can look like this. It can, you know, look like this, or it's basically a distribution of possible values of like a coin flip. Okay, so if you believe the coin flip lands heads 50% of the time, and you're quite certain about that, your distribution will probably look something like this. Meaning that you've got a very sharp peak at 0.5 and nothing else. And if you're absolutely convinced that coin flips always land heads with probability 0.5 and there's no other possibility, then you would just have a spike exactly at 0.5 and nowhere else. Okay, if that's your prior belief. And then if you have no other options for your prior beliefs and no amount of data can convince you otherwise, then that's it. Okay, then your prior beliefs will not change. Okay, but if you allow just basically something non-zero, then with an overwhelming amount of data and evidence, then your prior beliefs can be shifted. Okay, but that's what we have. So we have the Bernoulli distribution and the beta distribution with parameters a and b. Okay, and so so our posterior, without having to actually write this out, I'm just going to say this is going to be the Bernoulli distribution of our data, kind of the counts that we have. So yeah, Bernoulli distribution. So I'll just write Bernoulli. So the Bernoulli is the coin flip distribution, right? Bernoulli of basically our data given the theta parameter times the beta distribution, which is just going to be our prior distribution of theta, and the betas have the shape parameters a and b. Okay, so this is what we have. Bernoulli is, this is our posterior distribution of the theta given your data. That's what we have. Okay, so this is kind of, oh, and I'm sorry, I need to say this is proportional to this. Okay, because in the if it was the actual probability, we would have to divide by the probability of the data itself. All right, so this is the beta binomial model, and let me apply this kind of our Metropolis algorithm to this. Okay, and so the way the Metropolis algorithm works in the continuous case is that we now have what we call a proposal distribution. When we were talking about the island chains, how do we propose where to move? With the island chains, we propose where to move with just a coin flip. Yeah. If it landed heads, we would go to the right. If it landed tails, we'd go to the left. Okay. That was technically our proposal distribution. We flipped a coin and we'd say we either go over there or we go to the adjacent state to the left. Okay. So either, you know, with probability 1/2, we would go to state theta plus 1, and with probability half, we would go to state theta minus 1. Okay. And then we would move with kind of that move probability. Okay, with a continuous case, for the MCMC with the continuous case, we have what we call a proposal distribution. This is how we generate where we should move next. Okay, this is a way to generate the next step that we propose. Okay, and so what we have is, we're going to say x. Well, okay, I'm sorry. I'm going to say, so an example is, we can say our proposals, theta proposed, will come from a normal distribution that's centered at our current location. So our current theta, and we're going to propose something, and then we just have some value sigma. Okay, so currently, if my estimate of theta, if theta, this is my theta current, basically I'm going to propose something from the normal distribution centered at theta current. Okay, and so, you know, I might propose over here, or I could propose over here. You know, basically in R, we would just say theta dot proposed comes from R norm 1, and we plug in theta current and some sigma value. Okay, and so this will propose values to the right and to the left, you know, kind of with equal probability. And you can have different proposal distributions, but a lot of times the normal proposal works. Okay, so we just say, okay, we're going to propose a new location, And now the question is, should I move there? All right, and we're going to move there. The probability of moving is going to equal what? It's going to equal the minimum of 1, and we plug in f of theta proposed divided by f of the theta current. So in our beta binomial case, we just we plug it into the likelihood times the prior. Okay, and I don't need to worry about the marginal. I just need to figure out the numerator and the denominator, and I compare the ratio between those, right? And an e. And then we move that with that probability. Okay, so if the proposed location has a greater probability than the current location, then we're definitely moving there. And if the proposed location has a smaller probability, then we have to, what do? So if we get something here, what we do is we draw then kind of u from our unit. And what do we say? If u is less than probability move, then you move, okay? Which looks like theta current you take the proposed value and you make it your new current value. I'll say then rather than this arrow. Okay, and that's the Metropolis algorithm for the continuous case. So the biggest change here is that with the discrete islands, our proposal distribution was flipping a coin. When we flip the coin, we'd either go to the right or we go to the left. Okay. Now instead of flipping a coin, we have a continuous distribution, right? So now I can't just say I want to go plus 1. I mean plus 1 or minus 1 or something like that. It doesn't work because it's continuous. So now we draw from a continuous distribution to propose our next location. And so in that case, the normal distribution makes sense. But I mean, if you wanted to use another distribution that's continuous as your proposal, that's fine. Okay, but it's easy to propose values from the normal. So you just say, I need one new value, a random normal value centered at my current location, and we use some sigma value. That gives us our proposed value. We compare the probability of the proposed value, probability of the current value, and then we either move there or we don't, based on our probability of movement. Okay. Let me talk a little bit about this value sigma. Okay, and so here we have a nice illustration in the textbook. Okay, and so this is so in all of these cases, we're running the Metropolis algorithm. And we're trying to get the posterior distribution of the combination of our beta prior and our likelihood, which is based on the Bernoulli here. And so here we have a few options. So this is the standard deviation that we're using for a proposal. So in one case, we're using tiny standard deviations. Okay? When we use tiny standard deviations, that means, I'm currently centered, let's say I'm currently centered at like 0.6, then my proposed location might be like 0.61 or 0.62. Okay? And so when I compare the probability of my proposed location and the probability of my current location, because it's so close, that ratio is going to be pretty close to 1, right? If my, if you imagine just some current density, if I'm right here and my proposed location is right next to it, that probability of moving is going to be quite high. And so almost every single time my proposed location gets accepted. Okay, so you see just a tiny bit, a bunch of tiny little moves here. Okay, and that's fine. Okay, but the problem with something like that is there's a tendency to just kind of spend a whole lot of time in just one little zone here. Okay, it's kind of like putting an ant on a table, and I don't know, let's say you're able to track where this ant goes. Okay, you come back in an hour. Will the ant have explored the entire table? Probably not. Okay, or if it's explored an area, it's probably only explored just kind of like this thin little narrow path of places. Okay. On the other hand, we have a proposal standard deviation of 2. Okay, meaning it's proposing huge jumps. Okay, and so so what happens there is you're starting off at 0.6. It's going to propose something like maybe it proposes something like 1.2. Okay, well that's not going to get accepted, right? That's not even possible in the domain. Okay, or maybe it proposes something like 0.1. Okay, well that's going to get accepted with a very low probability. Okay, and so what you have here is your chain will propose a location and it will go there and then it'll get stuck there because every single place it's proposing, it's saying, hey, where should we go to next? Every single place that it proposes to go to next is like a bad suggestion. And so the algorithm's going to say, no, we can't go there, or I don't want to go there. And so you see the chain only goes in a few locations here. Okay, so it comes here, it gets stuck, and it's stuck there for like 20 iterations, and it proposes a huge jump, and it gets accepted, but then it's stuck there for like another 10 iterations. Okay, and it comes over here, and it's stuck here for like 40 iterations. Okay, so when you have too big of a proposal jump, the chain gets stuck in certain locations. Okay, and then so you're trying to find kind of the Goldilocks of your proposals, and so you want to propose a little bit over here, but not too close, so that you're not accepting every single suggestion, and you also get to explore the what do you call it, the locations quite well. Okay, so you get to explore the kind of the entire space of your distribution, as much as we'd like, and that's what we have. Okay, and here we have, there's this ratio. We look at kind of the acceptance ratio, the number accepted divided by the number proposed. And if we accept too many, if we accept like over 90% of those that we propose, this is generally not a good sign, because it means we're probably taking too many steps, and all of our locations are going to be very highly correlated with each other. Okay, and on the other hand, we're accepting hardly any. We have a very small acceptance ratio. That's undesirable. Ideally, we want something around half, around 50%. That's generally kind of the ideal acceptance ratio, where some are good, some are bad, and about we're suggesting about the right amount of variation. Okay, we'll stop here. We'll continue on Wednesday.